In this video, we're going to look at the Nobel Prize in Physics for the year 1907, awarded to Albert A. Michelson for his optical precision instruments and the spectroscopic and meteorological investigations carried out with their aid. Here you see some of the illustrations that go along with his Nobel Prize lecture. We will come to them in a minute. Same for these. This is the title of the lecture, Recent Advances in Spectroscopy. This is summarized by me, of course. In real, the lecture is longer. Start. Newton discovered the laws of gravitational astronomy, making calculations about all objects in the solar system possible. Newton also did important works in optics, separating the colors of sunlight, the foundation for spectroscopy. Spectroscopy made it possible to determine the physical and chemical constitution of heavenly bodies. When one narrows the aperture through which the sunlight falls on the prism, that would have sufficed to observe that the spectrum contains dark light. Fraunhofer discovered that fact by using a telescope and the slit and the prism, this creating the first spectroscope. The power of a telescope is measured by the closeness of the double stars it can resolve, so you could see them apart. The power of a spectroscope is measured by the closeness of double lines it can separate. First look at the left of the solar system. See figure 1. You can go back if you want to. Everything from line A to line H can be seen with the naked eye. Photography can extend this far beyond red and beyond the violet. In the yellow we observe line D, which can be linked to the element sodium. It is a double line. Using a better telescope, make the line pictured as further apart. This depends on the material of the prism, its size, and the numbers used. The best spectroscopers can resolve doubles, which are 30 to 40 times closer to each other as the double lines of sodium. The best spectroscope having a resolving power of about 40,000, which seems to be the limit under average conditions. Theoretically, there is no limit. Meanwhile, another device for analyzing light into its component parts has been found by Fraunhofer. It has superseded the prism, the diffraction grating. First use equidistant wires, later use gratings with lines carved on glass/gold left. Now the lines are graved into the glass with diamonds. Figure 2 shows a magnified cross-section of a diffraction grating, if you want to see it, go back, with light falling on it. The wave motion will pass through the apertures and will continue as a series of wave planes. All waves with a phase difference of 0, 1, 2, or 3 reinforce each other. See figure 3. In the direction of all the waves travel here will be an average on the screen. This direction is determined by the law of sinus alpha is m times L divided by S, with L is the length of the light wave and S is the distance between the gratings. And m is the number of the waves, always a whole number, 1, 2, 3, 4, etc. There will always be some light diffracted into other sections. There will also be waves that cancel each other out in the direction. These waves will be darkness. This is the case when the phase difference is a half, 3/3, 5/3, etc. And this is called a destructive interference. Now the difference between the two sodium lines is 1/1000 of wavelength. With a grating with n lines, will be total darkness into the direction corresponding to a retardation of m plus 1 divided by L. It means that when you want to resolve two lines, which 1,000 of wavelength apart, you will need a grating with 1,000 lines. The next direction, m is 2, which has a double retardation, the resolving power is 5. Call the order of direction m, then one comes to the formula R is m times n. Thus to find high resolving powers one needs to read many lines n and a high spectrum order m. Now this is 1907, we were able to mark 500 to 1,000 lines per millimeter. This was until Rutherford 1886, and now we have 2,000 lines on 2 inches. Roland made 100,000 lines on 6 inches, being able to distinguish between that. They were 100 times closer than the lines of sodium. The great difficulty is to have an absolute uniformity in the grazing space, which is difficult to achieve. Spectrum analysis of the light becomes increasingly important. It is used to investigate the effects of temperature, pressure, and magnetic field. Therefore, now gratings are used to have a resolving power of about 220,000 in the second order. The effect produced at the focus of the telescope depends on the interference of the trains of light waves. Newton again was the first to observe the interference of light waves. A slight moderation of Newton's rings to lead to a third method of spectrum analysis is less convenient but more powerful. When sodium light falls on two parallel glass surfaces, the light diffracted by the two surfaces will interfere. We will see a series of concentric rings, alternatively bright and dark according to the relative retardations of the two reflective beams. When the distance between the surfaces is made larger, the number of alterations increases. The number of these alterations corresponds exactly to the number of light waves in twice the increase in distance. It makes it possible to measure wavelengths exactly in this way. The measurements are also used to replace the arbitrary standard of length with a non-arbitrary one. Attempts have been made to do so, but the measurements contained errors. In the future, these errors may be eliminated and exact length standards be established. It is also not easy to account for alterations of light and darkness. This because of the defect in the homogeneity of the light deployed. This causes indistinctness of the interference range when the distance is greater than a few centimeters. The right light emitted by luminous vapor of metallic cadmium is best adapted. Different observers in different times with different equipment came to almost identical results. Maybe this can be used to establish a new standard for length in the future. The interference method can give information concerning the distribution of light in an approximate homogeneous source, while a spectroscope cannot. The interference method shows that if we are dealing with a double source or not, no spectroscope can do that. So extra double lines, which therefore were regarded as single lines, were discovered in Valium and in mercury. Double lines with an interdistance of 1 divided by 1,000 of the sodium lines can be found. Figure 5 shows such an apparatus. An ordinary spectroscope gives a preliminary lens of light. Then the interferometer is used to get a more detailed look. Examination of a group of lines may require many observations, and thus time during with light must stay the same. Good results were achieved when studying the Siemens effect. A new application is the echelon, a diffraction grating with a very high resolving power using a high order of spectrum. The retardation must be kept constant, and one lets light fall on a pole of parallel equally thick glasses. See figure 6 if you want to look at the cubic. If the line has 40 plates, each 1 centimeter thick, the retardation is about 10,000 light waves. The resolving power is thus, therefore, 40 times 10,000. The number of the plate can increase until absorption of the light by the glass gives a limit. A difficulty is the loss of light reflecting by the many surfaces. Twyman overcame this by pressing the plates together. The reflection vanishes. Another way is to silver the plates, giving more reflection and less absorbing. 4 times higher resolving power. The efficiency of the echelon spectroscope is shown by photographs 7 to 9, showing all the vapor. Figure 7 gives the second order spectrum of the diffraction grating of the largest existing size. And figure 8 by an echelon of 30 plates, each 7 meter thick, and figure 9 by an echelon of 40 plates, each 30 meters thick. The echelon spectra are separated. A1 and A2 are two spectra of the same line, Overlapping of these can be done by separating the spectra with a prism. Eventually, the prism can be replaced when needed by a grating. See Figure 10. Figure A shows a photograph of an ion spectrum using grating of an electron. Figure 12, the same for a sun spectrum. The combination gives the best results, the best accurate wavelength measures. Well, here you see again some pictures about the same. If you want to study them, pause the video and read the comment. Here you see destructive and constructive information. And here you see another experiment done by the Nobel Prize laureate. Maybe it's good to go back to these pictures again. So, if you want to study them further, you can also go to the original Nobel Prize lecture. You can follow the link, which is also in the description of under the video. Yeah. Okay. For now, thank you for watching. And next week, we will go to the year 1908.